Hello, everyone. I'm William Lee. I'm a professor at UNAM in Mexico City. I'm very pleased to introduce our next speaker, Jonelle Walsh. Jonelle is assistant professor of physics and astronomy at Texas A&M, where she works on the coevolution of supermassive black holes and galaxies, primarily from an observational point of view, analyzing stellar and gas dynamics near those black holes, with facilities from the optical to the radio and comparing these with numerical models. Today, Jonelle will be telling us about AG and mass measurements in the context of her work. Go ahead, Jonelle.
So I'm going to be talking about mass measurements of black holes, and in particular, focusing on dynamical methods applied to nearby galaxies. So supermassive black holes are found at the centers of essentially every massive galaxy, and it's become increasingly clear that black holes are very important components of galaxies. We now have strong pieces of evidence for the presence of supermassive black holes. And in the case of our own galaxy, that comes from tracking the paths of individual stars as they orbit close to the black hole. Beyond the Milky Way, black holes have been dynamically detected in about 100 galaxies to date. So there are three main ways to directly measure black hole masses, and they involve modeling the observed kinematics of stars, ionized, but now also molecular gas disks, and water maser disks. So stellar dynamical modeling is the most widely used method, since the motions of stars always reflect the underlying gravitational potential. However, extracting a secure black hole mass measurement from the observed kinematics is challenging just due to the complexity of the models. The models can also be subject to a number of systematic effects, such as mass degeneracies between the black hole, stars, and dark matter, as well as assumptions that are made about the intrinsic shape of the galaxy, like whether it's axisymmetric or triaxial. In contrast, gas dynamical modeling is conceptually simple, but gas can be influenced by non-gravitational forces, and so the main assumption of circular rotation needs to be verified. Also, many of the observed, at least ionized gas disks, show velocity dispersions in excess of what you would expect from just bulk rotational motion alone. This intrinsic velocity dispersion could be dynamically important, and if so, it should somehow be included in the models in order to prevent a biased black hole mass measurement. And so in a few cases, black hole masses have also been measured using megamaser disks in active galaxies. This technique provides strong black hole mass constraints, as we're talking about sub-parsec scale circumnuclear disks that reside deep within the gravitational potential of the black hole. Unfortunately, such disks are rare and require special physical conditions and nearly edge-on inclinations in order to reduce the maser amplification. There can also be departures from Keplerian rotation due to significant contributions from the disks themselves. So getting precise black hole mass measurements really boils down to getting high angular resolution observations that probe the innermost regions of galaxies where the gravitational potential from the black hole dominates. So that region is the black hole sphere of influence, and its size is pretty small, typically on the order of tens of parsecs. So the Hubble Space Telescope, with its great angular resolution, has therefore played a fundamental role in detecting black holes in a large number of galaxies. More recently, though, significant progress has been made using adaptive optics, AO, on large ground-based telescopes. And now ALMA provides this exciting opportunity to directly detect molecular gas within the black hole sphere of influence of nearby galaxies, given its superb angular resolution and sensitivity. So even though the black hole's gravitational influence is limited to the innermost regions of galaxies, surprisingly, the masses of black holes correlate with the large-scale properties of the host galaxy. So two such relations are the M sigma and the ML relations. These relations suggest that black holes and galaxies grow in tandem. However, it remains unclear exactly what role black holes play in galaxy evolution and what the primary physical mechanisms are that drive these empirical correlations. In order to answer these questions, we need more robust black hole mass measurements, especially at the extremes of the black hole mass scale and over a wider range of galaxies that have experienced different growth pathways. So the approach I'm going to take with this talk is to highlight two of the main dynamical modeling techniques by discussing what I think are an interesting sample of galaxies that also allow us to start to take these necessary steps. So we're studying a sample of local compact galaxies. These are early type galaxies with small sizes and luminosities for their large stellar velocity dispersions. These compact galaxies are interesting because they could host some of the most massive black holes out there just based on their large stellar velocity dispersions. But they're very different from the kinds of galaxies you would actually expect to host the most massive black holes. So for example, I'm showing some galaxies in the Perseus cluster. NGC 1275 is the brightest galaxy of the cluster and is exactly the kind of galaxy you would expect to find at the upper end of the black hole scaling relations. Giant ellipticals and BCGs, like NGC 1275, are large in size, and they're often dispersion-supported objects showing little to no rotation. So that is in sharp contrast to NGC 1277, which is a compact galaxy. It's located nearby, and it's small and flattened and rapidly rotating. And instead, it looks quite similar to the typical massive quiescent galaxies at a redshift of about 2, the so-called red nuggets. So we acquired HST images, wide field spectroscopy, and AO observations from Gemini and Keck using integral field spectrographs. We have completed AO observations for 6 of the galaxies and have fully finished the analysis for 3 of them. From the IFU data, we extract spectra over a range of spatial locations, and we measure the line of sight velocity distribution of the stars, parametrized by the velocity dispersion, and then deviations from a Gaussian of that distribution. So for NGC 1277, we see from the velocity map that the galaxy is rotating quickly with velocities of plus and minus 350 kilometers per second. The velocity dispersion map shows this huge rise in the dispersion to values of about 550 kilometers per second at the nucleus. And we have similar kinematic maps for the other compact galaxies. So how this works is we construct orbit-based stellar dynamical models. The main idea is that the galaxy's gravitational potential consists of contributions from the black hole, stars, and dark matter. We set up a representative orbital library, and we integrate orbits in that potential. We assign weights to the orbits such that the superposition reproduces the observed kinematics and surface brightness. And then we just sample a whole bunch of different potentials, looking for a model that most closely matches the data. So when doing that, for NGC 1277, NGC 1271, and Mark 1216, we find some very massive black holes in the range of 3 to 5 times 10 to the 9 solar masses. These galaxies are consistent with M sigma, but are positive outliers from ML. And we're finishing up another stellar dynamical analysis for another similar galaxy, and we're finding the same behavior. So even when conservatively using the galaxy's total luminosity instead of the bulge luminosity, these galaxies are still clear outliers from ML. So the natural question is, how did such large black holes end up in relatively modest galaxies? One possibility is that we simply don't have enough mass measurements at the upper end of the black hole relations. Neither the form of the correlations nor the intrinsic scatter is well established in this high mass regime. So it's possible that the compact galaxies simply fall in the tails of a distribution between black hole masses and host galaxy properties that have yet to be fully fleshed out. Another possibility is an interesting one. As I mentioned before, these local compact galaxies look very similar to the redshift 2 red nuggets, and they could be relics. The redshift 2 red nuggets are thought to grow in size and mildly in mass through a series of mergers to produce the present-day massive early type galaxies. So perhaps our sample of local compact galaxies took a different evolutionary pathway, a more passive one. If true, then galaxies like NGC 1277 could reflect a previous time when the local ML relationship did not apply. Galaxies instead contained over massive black holes, and it was the growth of the host galaxy that had yet to catch up. In other words, it could suggest that black hole growth precedes that of the host galaxy. So far I've been talking about results from stellar dynamical models, but ALMA, or really radio observations, are beginning to play a key role in building up robust gas dynamical black hole mass measurements. So with ALMA's huge gain in sensitivity and angular resolution, we're able to routinely map molecular gas kinematics within the black hole sphere of influence and achieve the precision mass measurements necessary to advance the field. In addition, the radio observations trace the cold, dense molecular gas, which is likely to have a smaller turbulent velocity dispersion compared to the warmer ionized gas disks that so far have been the subject of nearly all of the gas dynamical black hole mass measurements. Therefore, one of the major systematics associated with gas dynamical modeling could be much less of a concern with radio observations. So it turns out that about half of the compact galaxies show these well-defined, regular-looking nuclear dust disks, and such dust morphology suggests the presence of cleanly rotating molecular gas, and therefore could provide us with the opportunity to derive gas dynamical black hole masses from ALMA observations. So with the exception of NGC 1277, none of these galaxies have been previously targeted with any millimeter or submillimeter facilities. So we didn't know what to expect for how bright the CO would be at the nucleus. Therefore, we obtained brief ALMA observations for 3 of the compact galaxies in order to first test for the presence of CO on scales comparable to the expected black hole sphere of influence. And so as you can see here, especially with these spatially resolved velocity maps, we indeed find nicely rotating CO disks. And my graduate student, Jonathan Cohen, has been working on modeling UGC 2698. So how the gas dynamical modeling works is that we assume a thin disk of gas in circular rotation. The galaxy's gravitational potential, again, consists of the stars.
1-minute warning, Jonelle.
Okay, thank you. So you're taking the projected stellar surface brightness and an assumed mass to light ratio, plus there's, of course, the black hole. During the modeling, we account for the beam smearing, and ultimately we're looking to compute a model cube that most closely matches the observed data cube. So when we do this for UGC 2698, this corner plot here basically summarizes our modeling results. We are finding a black hole mass at 2.4 times 10 to the 9 solar masses. We also explored the possible impact on the black hole mass if we change some of the inputs and the assumptions in the model. And then over here is a comparison between the observed line profile and the best fit model line profile for 2 different sides of the disk. Okay, so UGC 2698 is consistent with both the M sigma and ML relations. It's the largest and most luminous galaxy in our sample, so it's not quite as compact as the other galaxies. It's possible that this galaxy has experienced a little bit of growth relative to the others. Now, unlike UGC 2698, the M sigma and ML relations make very different predictions for the black holes in the 2 other galaxies we've observed with ALMA. So it'll be interesting to see where those galaxies fall on the black hole relations once we actually have gas dynamical masses for them. And I kind of want to wrap up here by highlighting the exciting avenue that ALMA really has opened up for the field using this measurement by my postdoc, Ben Bozell. So NGC 3258 is a nearby elliptical galaxy. It's not a compact galaxy. We got beautiful 0.1 arcsecond resolution observations in cycle 4 with ALMA that highly resolve the black hole sphere of influence. And so you can most easily see that by looking at the position velocity diagram. So these Keplerian upturns here are very, very clear. So we fit gas dynamical models, and we even allowed for a slight warp in the disk and found a high mass black hole with a mass of 2.2 times 10 to the 9 solar masses, with a statistical uncertainty of just 0.2%, an estimated systematic uncertainty of about 6.6%, and a 12% uncertainty due to the distance. So this is the most precise black hole mass measurement made to date for any early type galaxy, and is beginning to rival some of the maser black hole mass measurements that have been made in spiral galaxies. So to briefly conclude here, we really need more black hole mass measurements, especially at the extremes of the black hole mass scale and over a wider range of galaxies that have experienced different growth histories. Using AO observations and stellar dynamical modeling, we're finding large black holes in a sample of local compact galaxies that could hint that black hole growth precedes that of the host galaxy. ALMA provides this new and exciting opportunity to robustly and precisely measure black hole masses through gas dynamical methods. And this is across the Hubble sequence, both for low and high mass black holes. And we're using this method for some of the compact galaxies as well, and studying other nearby massive early type galaxies. Thanks.
Thank you, Jonelle. We have time for a quick question. Demosthenes Kazanas is asking, if by compact galaxies, do you mean high density or just normal density but small size, implying a small total galactic mass?
Yeah, so what I really mean by that are galaxies that are small in size in terms of their effective radius, but are massive. So I'm talking about effective radii that are about 1 to 3 kiloparsecs, and then stellar masses that are about 10 to the 11 solar masses. So very unusual in the nearby universe, but very similar to those red nuggets that I was talking about, that these massive quiescent galaxies that are redshifted to.
All right. Thank you very much.